Okay, time to get started. So last time we finished by stating our sort of general form of the chain rule. So the big idea of the chain rule is this right here. So the act of differentiation turns a composition right into a product. Or said differently, the derivative of a composition is the product of the individual derivatives. Okay, so notice as well what we have here. This is a statement about derivatives. Just remember that now derivatives are matrices, right? It's easy to lose track of this and to think of derivatives as, you know, fundamentally being partial derivatives. And again, you may recall I kind of warned against that, right? Partial derivatives we cover first for reasons that are, I think, kind of sketchy. But nevertheless, we're kind of forced into it. Derivatives, you have to make sure to remember when you say derivative. Really, the best way to think about that is as matrices. So, product of derivatives is what we're talking about here. Okay, all right. So let's see an example. So we have here a couple of functions, and you'll notice that this first function f turns the x variables into y variables. That's what f does. And then the next function turns those y variables into z variables. All right, so f goes first and then g goes second. And you'll notice that a bunch of information is given. We'll use that information as needed. What we've been asked to compute here is the derivative of the composition. And now I've given you all this warning already, but let me make sure you're noticing f acts first. Right? And again, that's implied by the way the variables are written down here. F acts first and then g acts second. And when you compose functions, awkwardly, the one that acts first is on the right, not on the left. So heads up, you always got to be on the lookout for that. And again, School of Hard Knocks and all that. Okay, so how do you find the derivative of this composition? Well, we have an explicit formula on the previous page. Derivative of the composition is the product of the derivatives. Cool. All right, well, let's start plugging stuff in. Let's see, apparently the first thing we're going to need here is the derivative of the f function at the point 1, 2. And wouldn't you know it, lo and behold, that was given. So cool, so we write that down. Sometimes you have exactly what you need. Life is good. Okay, next, we need the derivative of g evaluated at this point called f of 1, 2. Now, that's the deal here, right? That's what the derivative matrix, the chain rule says. The derivative of the second function is evaluated at, the point where g is acting, and g is acting at the point f of a. So I need the DG matrix at the point f of 1, 2. I have the DG matrix at the point 3, 1, 0. At an immediate glance, it's not necessarily clear that those are the same until you notice that we'll again conveniently lucky break. It is exactly the other piece of information that we were given. Right? So that first equation that we're given over here, f of 1, 2 of 3, 1, 0, is what allows us to realize that the matrix we were given is the matrix that we need. All right, is everybody on board? And thus, by the way, that goes there. Okay, and now it's just a matter of multiplying it out, and I know you all can multiply matrices. I do want to point out something about the way this example is written. There was a deliberate landmine, kind of, in the statement of this question. I've done this on exams before as well. And again, keep in mind, there is an important worry you have to always be worried about, which is, wait a minute, which one's first? Right? And is it left to right, or is it right to left? And it depends on whether you're talking about a diagram or notation. Or you got to be careful with this, right? So the little dirty trick that I pulled here is the one that I listed first. I listed it in the givens on the left, but it goes on the right. Right? And the one that I gave you on the right actually goes on the left. Right? And so I did this as a way, well, if this had been an exam question, and again, I've done this on exams as well, this would be a way of catching and seeing who's actually being careful about this kind of thing, because you have to be. And by the way, I do it because life will do it to you about half the time, right? So you have to be really careful about that kind of thing. Does that make sense to everybody? Everybody on board? Okay. All right. Okay, now you'll notice the second part of the question here. And actually, I think I'm going to zoom out so I can get this all on the screen at the same time. The second part of the question asks for this partial derivative right there, partial of z3 with respect to x1. Notice that z3 is one of these eventual output variables. And notice that x1 is one of my original input variables. So what I've been asked here is a partial derivative in the composition. It's not a partial derivative in any one of the original functions. This is a partial derivative in the composition. So I'm going to find this entry, this partial derivative I want as one of the elements of the matrix that I just computed. It's going to be somewhere in here. Well, I wanted that in purple. It's going to be somewhere in here. We just have to find which of those numbers it is. Now, we have rules, right? There's an explicit and important structure for how we write down derivative matrices, and we talked through this previously. And you remember that output variables correspond to rows. You got to make a conscious effort to be careful in thinking about how you write down your derivative matrices. So we have been asked for a partial of the third output variable. That means that we are looking for an element in the third row. Now, likewise, input variables correspond to columns. We're looking for the partial derivative with respect to apparently the first input variable. That means we're looking for an element in the first column. And so that narrows it down for us. That helps us realize that we are looking for that element right there, and the partial derivative we're looking for is 3. Yeah.
How did you even know that this partial derivative was used in combination with the composition derivative?
Yeah. So the function, right? The function f takes in x variables and gives out y variables. This isn't one of those, right? This has z as the output, right? The g function gives the z's as outputs, right? But it's taking as inputs just the y variables. This wants a partial with respect to x. Okay. And so if z is an output, and if one of the z's is the output and one of the x's is the input, that's only makes sense if you're talking about the composition. Is that cool? Yeah. Yeah. Okay. Yeah.
I just want to understand what a partial of a variable means as opposed to a function.
Oh, yeah. I mean, it's arguably an abuse of notation here, but if we have a function called f, right? We arguably I should say a partial of the third component of the composition, right? But it's just that we already have a name given for that third component, and so it is arguably a little bit sloppy, but it's pretty standard. Everybody knows what the user meant when this kind of convenience is taken advantage of. Yeah, is that cool? Yeah. All right. Okay. Cool. All right. Real quick, some special cases I want to talk about to the chain rule. Keep in mind, our chain rule is a statement about composing multivariable function. Let me go back to it real quick. Here you go. It's a statement about composing multivariable functions, right? I have a function here, several in, several out, and I have a function here, several in, several out. Okay. That I'm composing. So we're going to consider now how would things change if, in fact, when I'm composing two functions, what if one of them, what if the first one has only a single input variable? And I mean, the theorem still works, no question as to whether it works, but what's the kind of the convenient punchline? You know, how do things simplify, or what is this special case? And I'm going to reconsider my color choice. I'm going to use yellow. All right, so in that case, let's think about what this function here is. This is no longer a function with several inputs and several outputs. This is now a function with one input and several outputs. Let me say that differently. Position in Rn is a function of one variable. Position as a function of a single variable, that's kind of rings a bell, right? Smacks of position as a function of time. And when you have position as a function of time, we understand what a derivative means there. A derivative is a velocity vector. And in fact, with, as you see here, only one input variable, the derivative matrix has only one column, and it is literally the velocity vector of that first function. Everybody with me? All right, now likewise, let's think about the composition. The composition there, how about it? Again, it's position, this time position in Rm as a function of time. So same deal. One input variable means that there is only one column, and again, we have a notion of what it means to talk about the derivative of a parametric curve, this time y as a function of t. And so this derivative matrix is in fact just the velocity of that parametric curve. So what's going on here then is the nice interpretation in this circumstance, because the original input variable is just one, that I'm going to think of as being time. What we have here is an interpretation about what the derivative matrix of f does. And this actually is an old fact that we've talked about before. I just like it when old news that we already understood shows up again, right? It's kind of a nice sort of confirmation. This says that the derivative matrix of f is what you multiply by input velocity to get output velocity, right? So this green vector here represents velocity in the domain of f, and this blue vector here represents the velocity of the image in the target. So input velocity to output velocity, yeah.
So in this case, is the first function where it's R1 to Rn, is that the same as a parameterization?
Yeah. So both the green function and the blue function are parameterizations. Yeah, that's right. So here, let me draw a picture of what this might look like. Sort of a diagram. I'm going to say we have a domain there and a target there, and f is this function that goes from the one to the other. So this is a picture of the f function, and we have the green function is a parametric curve moving through the domain, and the blue function is the image of that, which is going to be some sort of a parametric curve moving through the target. Yep. Everybody happy? Okay. All right. So, example. And again, this restates old news. Where's my cursor? I can't. Oh, there it is. Okay. So, quick example. We've got some function given, and that's this function here. And we're given some input velocity. Given. Okay. The question that we've been asked it says here, compute df dt. Well, that's going to be the output velocity. And if you want to compute an output velocity and you've been given an input velocity, we use this formula. That output velocity that I want is going to be the derivative matrix, which you'll notice I have to go to some trouble to compute, right? Derivative matrix multiplied by the input velocity, which again we were given. It's 4.3. So that's straight, immediate, right down the pipe application. Everybody okay? All right. Okay, special case of a special case now. What happens if not only do we have a single original input variable, how does everything change if I also have just a single eventual output variable as well? Well, that changes just the one thing. By the way, it remains that I have a parametric curve for the first function, and that's the velocity of the parametric curve. That's all the same. And this is, again, a composition is also a kind of it's a parametric curve on the real line. It's kind of a weird concept, I suppose, but it's just some y is just a point kind of moving around on the real number line, and so the left side is that derivative. What changes is that this function, whose derivative matrix is like this, because that now has only a single output variable, this derivative matrix only has a single row. And you may recall that when the derivative matrix only has a single row, multiplication by that matrix is morally equivalent to dot product with the gradient, which is kind of the same, isn't it? Right? This matrix is a matrix whose entries are all the various partials. The gradient is a vector whose entries are the exact same partials. Right? So the two different ways that I've got this written down are, they're algebraically kind of slightly different, but in terms of how it cranks out, it's all exactly the same. I'm taking these elements, multiplying them by these elements, and then adding. And whether you want to view that as a matrix product or a dot product, whatever, right? Two different ways of looking at ultimately the same thing. So the result of this special case is that you have the choice to reinterpret as dot product with the gradient instead of using a derivative matrix. Sometimes that's convenient for various different reasons. So example here, and again, this is it's a pretty straight up example. We've been asked to find a derivative of a composition. You'll notice here we have t as a function of x, y, and z. And then you'll also notice that here, that's not what I meant to do. Let's see here. There we go. Here I have, in a way, describing the bird's location as a function of time, right? We're talking about its current position and how it's moving. That means x, y, and z are functions of t. And so the question has asked the derivative of temperature with respect to time. You'll notice that is the composition derivative. Right, so we can use the special case of the special case formula on the previous page that says that derivative is computed with a dot product with the gradient. Is everybody happy with that? Yep.
So how did you make the assumption that we could go from the x, y, z to the temperature?
Oh, because it says, let's see here, right here, that temperature is a function of x, y, and z.
And
Yeah. Yeah.
I get. And how would velocity play a role in any of that?
Yeah. So this is this up here is telling me that position is a function of time. Now it's describing the position as a function of time in a kind of a non-formulaic way. It's saying, well, at a certain moment, this is where I am, and this is how I'm moving. But if you think about it, that's just a discussion of how position is changing as a function of time. Is that?
Okay.
Does that make sense?
I think so. Yeah. Yes.
Okay. Yeah. Okay. Cool. So a couple special cases. Really, though, keep in mind, all of this comes out of this original point of view on what the chain rule says. The chain rule is a statement about how the derivative of a composition is the product of the individual derivatives. This is the sort of the most general, really the best way. If you're going to pick a cornerstone point of view on the chain rule, this should be it, right? Because everything comes from this one point of view. All righty. So now I'm going to give you a different point of view. Convenient, surprisingly often. Even though I don't think this is the best cornerstone point of view on the chain rule, but in practice, very often this is really nice. So here we go. Notice I'm composing functions. I have x variables go into the function f and out come y variables, and here's that derivative matrix of which I've made a few entries. And then the y variables that came out of f, you'll notice that those are the inputs into this function g that spits out z variables. And here again is the derivative matrix for that with a few entries noted. So all together, if I want to understand the composition taking in x's and spitting out z's, that's going to have a derivative matrix that has these kinds of partials as its entries. And again, matrix form, the chain rule, it's going to be the product of these two original matrices. And again, note the green-blue switch, right? So heads up, be careful. It's important to always keep that straight. Okay. All right. Now, having noticed that, let's suppose that you don't actually need the whole matrix. What if you only need just that one element of the product? I just need to know the one partial derivative. I don't need all the other partial derivatives. I just want to know just the one. Right? And I don't want to have to write down the whole matrix here and the whole matrix there. Let's just streamline it. If I only need that one entry, look, that one entry, we know how matrix multiplication works, and it's a dot product of these entries with those entries, right? The corresponding row of the left matrix dotted with the corresponding column of the right matrix, right? That's how we find elements of the products. And you can just multiply that on out, right? And here you go. You get, there's those blue entries, how they show up. And here's how the green entries show up. And lo and behold, we have ourselves a formula that computes a single partial derivative as streamlined as possible. And notice we get to ignore all of that and all of this and all of that and all of that if there's anything over there. And I don't have to compute any of the rest of all of that. So just bare minimum, totally streamlined, exactly what we need. If what we need is just a single partial derivative. Everybody on board? All right. Okay, bunch of stuff to say about this. We're going to do examples and special cases and landmines and stuff like that. But I do want to start with a landmine. A lot of students will look at this formula here, and in particular will see this one term right there, and will think to themselves, oh, hey, check it out. I can just can I just cancel the partial y1s? Right? You see the temptation. They do this in single variable calculus classes a lot. In single variable calculus classes, there's a point of view by which this is actually a reasonable thing to It is not in a multivariable case. The point here that doesn't come up in single variable is that this thing here is part of a story, right? This thing that I would, in the denominator, that I would kind of like to cancel with this over here. That partial y1 is part of a story, and this partial y1 over here is part of a different story. It's a completely different scenario. So even though, tragically, we use the same notation to represent these two things, they're the same notation in completely different scenarios. They're just not the same thing. It's kind of like if there's an x in, question 6 on the homework, and then, in question 48 on the homework, there's also an x. Yeah, they're different questions. Those x's are unrelated, right? That makes sense? So I claim the same thing is going on here. Now, in order for me to show you how it is that those are different scenarios, I'm going to use this handy diagram I already have written here. I'm going to temporarily scratch off this stuff. We will talk about all this stuff later, as in about 3 minutes. But let's look just at that diagram, and let's look at, let's see here, let's look at this partial y1 right here. Partial y1. As part of taking a partial derivative with respect to xj. Now I'm going to represent that on this diagram down here. Partial derivative with respect to xj says that's going to be my variable, taking the partial of y1, but specifically it being a partial, that means that these other variables over here are constants. Yeah? Everybody cool? That's how partial derivatives work. Here's the thing. If xj is changing, notice xj doesn't just affect y1, it also affects a bunch of other variables also. So in this scenario where xj is changing, yeah, y1 is changing, but so are all the other y's. Right? So these are not constants. These variables over here are changing, presumably, as well. Button, there it is. Okay, is everybody with me? Okay, now let's look at the other scenario. The other scenario here, let's, trying to understand what does this y1 mean. That y1, different story. We're looking at the partial of zi with respect to y1. How do partial derivatives work? Partial derivatives work by saying, okay, I want to understand how this changes as that changes, and all of the other input variables have to be held constant. And that's the problem, right? Talking about this partial derivative of zi with respect to y1, talking about that as a partial derivative requires that these subsequent y variables be constant. Whereas in the other scenario, it was unavoidable that those variables are going to be changing. These are incompatible scenarios. So they're just different stories. They're different cases, and as such, you just cannot cancel. There is no. Let's see here. How do I okay, so I'm going to put a cross, an X through the cancellation, right? You cannot cancel those partial y1s. Everybody okay with that? By the way, good thing that you can't. Check it out. If you look at this formula, if you could cancel these, notice that partial xj is right there. This partial zi is right there. If you could cancel those, then this would already equal to that, and that would bring up the question of what's going on with all these other terms, right? That would be bad. Yeah? Everybody see the issue? Okay. All right. Okay. All right, so don't make that mistake easy. You'd be surprised how often it is. I have students every year that will write down this as the chain rule, and will even helpfully draw the little X through, the little slash through those, and this that makes no sense. This is a fundamentally inaccurate point of view on the chain rule. All right. Okay, so yeah, now back to this page. Let's try to make sense out of our equation that we've written down, our very convenient single equation, avoiding matrices. Isn't that nice? How does this make sense on the diagram? Okay, keep in mind, xj is changing. I want to keep track of how zi is changing. Roughly speaking, the big idea here is that as xj changes, well, if you change this variable, that's going to cause y1 to change. It's also going to cause y2 to change. Blah, blah, blah down the line. It's going to make all these different y variables change, and each one of those by itself, let's think about what happened when y1 changes. If y1 changes, the mere fact of y1 changing, setting aside that, yeah, the other y's are changing too, the mere fact of y1 changing will cause changes in zi. And then also the mere fact of y2 changing will cause changes in zi, etc. Right? And what you're going to notice is that this arrow lines up perfectly with that factor. This arrow lines up perfectly with that factor, and therefore altogether this path, you might say, the path through y1, this is a path along which changes can propagate from xj to zi, and that path corresponds to this term in our coordinate chain. And likewise for the other terms, and so in the same sense that this path corresponds to that term, likewise on down for the rest of them, and then let's see here, then this path corresponds to that term. So I think it's a really nice point of view. This our formula here, again, this came straight out of our matrix, sort of cornerstone point of view on the chain rule. But I can think of it in terms of the various different paths along which these little, as xj wiggles, then it's going to make all of these wiggle as well, and that all those changes just propagate through these different paths, and each path gives you a term. And a very convenient way to sort of think through, this formula, how to come up with, if you will, this formula without having to bother with writing down the whole matrix form. Okay, and then the last little tweak, what I've got here, what I've persuaded you, I hope, is that your formula relates paths to terms, but notice that every path corresponds to what I'm going to call an intermediate variable, right? Each one of these paths goes by way of one of these y variables. It's we call them intermediate variables because they're kind of halfway in between, right? They're not the original inputs, they're not the eventual outputs, they're just intermediate. So each intermediate variable gives you a path, each path gives you a term. Now let me show you how we can put that into practice. So this example here, notice we have a couple of functions given. I've got this function f that takes x's as its inputs, gives you y's as its outputs. I've indicated thusly on the diagram. Okay. Now I've got this second function here that takes y's as the inputs and gives you z's as the outputs. And so again, correspondingly, right, on the diagram there, this is our little road map of which variables relate to which other variables in which way, and what's a function of what, and that kind of thing, right? Okay, I've been asked to compute, it says here, the partial of z2 with respect to x2. And okay, that's a composition partial derivative, and using this idea of intermediate variables, well, there's two intermediate variables here. There's what you might call the y1 intermediate variable that gives you what you might call the y1 term in what is going to be our sort of coordinate chain rule here. And then there is this y2 path through the y2 intermediate variable, which gives you our y2 term down here in our chain rule formula. And that allows us to compute this thing as desired. Is everybody happy? Okay. It's a really nice trick. Notice I didn't write down any derivative matrices. That's a nice hack, right? We totally bypassed the inconvenience of having to write down those matrices, even though, keep in mind, I mean, where did the chain rule originally come from? And I know I keep going back to this, right? But really important point. If we're going to write down a chain rule, our notion of the chain rule comes from looking at compositions of multivariable functions and interpreting that composition as making a statement about products of derivative matrices, right? And here we just get down to the same result by looking at variables and paths and easier things to write down. Okay. Everybody happy? Okay. All right. Now there's a couple of sticky wickets that you have to worry about. Confusion of variables is annoying. Now, oh man. It's annoying, but I know you all know single variable calculus, so I'm going to go real quick through this. Here's a couple of single variable functions, right? X squared, x cubed, no problem. Easy single variable functions. Let's find the derivative of the composition. Now I'm going to do this problem three different ways: a wrong answer, an acceptable way, and then what I think is really the way everyone should do it. So what's wrong is to be a little too casual with how you write down the chain rule, right? You're getting a little too happy about the fact that we know the derivative of a composition is the product of the individual derivatives. You just kind of write that down a little too fast and loose, right? And then say, all right, well, look, check it out. G prime is 3x squared, and f prime is 2x, blah, blah, and notice wrong answer. Wrong because, of course, right? Here's the more careful writing of the chain rule. Yeah, the derivative of a composition is the product of the derivatives. Yes, sure. But G prime has to be evaluated at f of x, not at x. And this was a frustration for me when I was learning single variable calculus, whenever that was. And I was like, why? It just seems weird to plug in something other than x there because, look, g is a function of x. Why would I plug in f of x? Seems mysterious to me, right? But notice that makes it work because if g is the cubing function, then g prime is 3 times the squaring function, and plugging in f of x gives you x squared squared, which, again, the rest of the algebra makes it all work out correctly. Is that cool? I think both of these solutions are just the wrong way to come at it. Let me show you what I think is the much better way to come at it, and that is to recognize that while there was nothing wrong with writing down f of x equals x squared, that's perfectly legal, perfectly fine, no problem. And while there was nothing wrong with writing down g of x equals x cubed, perfectly legal, not a problem, fine. The very moment that we make a reference to composing these functions, we have a problem, right? Because what this composition means that what comes out of F has to be the thing that goes in to G. And if I start to kind of write that down and think about it, right? What comes out of F? Oh, whoops. What comes out of F? What am I going to call the thing that comes out of F? I'm not going to call it X. X is what went into F. The thing that comes out of F, I can't call X. So I'm going to call it something different. I guess I'll call it Y. And as soon as you say that, and again, with the understanding that we're composing functions, if the thing that comes out of F is called Y, then really the thing that goes into G should also be called Y. That's what composing is. The thing that comes out of F is the thing that goes into G. So that means I really should, first cat out of the bag, I should rewrite this function in terms of Y. That's just a dummy variable. Right? You use any variable you want, it doesn't matter. I didn't change the function G. Right? I'm just writing it in terms of a variable that avoids what I would call a confusion of variables, right? I mean, it's real weird to have the thing that goes into G be called X because X is over here, not over here. It just doesn't make any sense. And if you make that change, now again, that's one little tweak, right? A little teeny tiny little tweak there. You make that change, and all of a sudden now you can just be as casual as you want here. And look at this. I'm writing down the chain rule. Again, super casually, derivative of compositions, product of the derivatives. Careless about where am I evaluating what, right? And yet, G prime, I write down casually 3y squared. F prime, I write down casually 2x. You multiply that out, you get that, and now the notation is giving me an immediate little reminder that, oh yeah, I got to figure out what that y thing is. This y thing here is, I need my answer to be in terms of x, so what the heck is y? Well, y is the thing that comes out of f. Y is x squared. So plug it in and we get the correct answer. No confusion of variables, no having to remember, oh yeah, you got to plug in f of x instead of x and all that, that mystery, right? That's all just, unfortunate consequences of making an unfortunate choice about which functions are written in terms of which variables. Okay, is everybody okay with this? You see how life becomes so much easier when you just avoid confusion of variables in the first place. Okay, I start this as a discussion about single variable because it's so much easier to see what goes wrong and how things are improved by avoiding confusion of variables. This, of course, is a multivariable calculus class, and that's my real motivation here, is to point out that the same worry comes up in multivariable, and we have the same solution. A couple of functions given, both written in terms of x and y. No problem, perfectly legal, not an issue at all, until I decide to compose them. Now I've got a confusion of variables problem, and I have to fix it as follows. F is written as a function of x and y, which is fine, but the things that come out of f, I can't call them x and y, of course. I've got to call them something else. I don't know, let's call them u and v, not that it matters. Okay, well, once you've decided u and v are the things that come out of f, then u and v had better be the things that go into g. That means I need to rewrite g in terms of u and v instead of x and y. Everybody follow that? Morally the same situation and treatment that we saw previously. And now that we've done this, right, we look back at the statement of the question. The original statement of the question was all of this. We throw that away, right? We've got a much better choice of how to write G now. And now, yeah, you just follow the rules. Nothing too tricky here. Derivative matrix for F, derivative matrix for G. Derivative of the composition is the product of the derivatives. Again, don't worry about what's evaluated where. The choices of our notation will keep track of that for us. Just write them down, right? And in particular, notice that our answer has U's and V's in it. And what am I going to do with that U right there? Well, what's that, right? The composition is a function of x and y. I need to figure out how to get rid of this u. I need to rewrite u in terms of x and y. And notice u, being as it is the first input for G, it is correspondingly the first output from F. And so u is x squared plus y squared, and likewise v, this v right there that showed up, v being the second input to G is the second output from x, x squared minus y squared. And then you can multiply those matrices. Pretty happy? Annoying, but you got to be careful with this kind of thing. The interesting part is that in practice, everybody knows about single variable issues. Most people do it this way that I have labeled as valid. Right? Most people do like that, and they just remember this part. But it's really hard to remember it here because there's so much else going on. All right, last thing I want to point out, and this is a situation that comes up again surprisingly often. We have this thing called the chain rule, and everything that we know about the chain rule relates to compositions of functions, and these are very precisely defined concepts. What is a function, right? That is there's no flexibility on that, right? And what does it mean to compose functions? Well, that's a very precise thing. So the issue that I'm worried about here is that notice when you have a couple of functions that you compose, that gives rise to a diagram, but it gives rise to a very special kind of diagram. It gives rise to a diagram every time you have a composition. You get a diagram where the outputs from sort of the left function are the inputs to what you might call the right function. And there's no confusion of variables, and the inputs from the one are the outputs from the other, and stuff like that, right? So a lot of students make the mistake of thinking, oh, well, whatever, I can use any diagram I want, and you can't. Specifically and importantly, everything we know about the chain rule, again, comes from this formula where we're composing multivariable functions. So when you find yourself looking at, where am I? Yeah, here we go. If you're looking at something like this, if you have a bunch of equations and you just kind of toss together a diagram that looks something like this, yeah, cool, because that literally is a composition of functions. Here's the first function, and here's the second function, and everything makes sense. All the variables have distinct names, and the outputs from the first function are the inputs to the second function. Everything's fine, no problem. But what if you have a bunch of equations that look like this down here? The example that we're going to do next, which will be Wednesday. But if these are your equations, and if you kind of draw the corresponding diagram, your diagram's going to look like that. What the heck is that? That is not a composition of functions as written. We don't have a chain rule for random diagram that you write down from some equations. We just don't have that. We have a chain rule for compositions of functions. So in a scenario like this, we don't have a rule for this, and in fact, it's not even clear, for example, what does this mean? What does it mean to take the partial of z1 with respect to x1? z1 is a function of, it seems, 3 different variables. If I'm going to take the partial with respect to x1, that means that x1 is going to be my variable, and I'm supposed to hold y1 and y2 constant. But check it out, I can't. I can't hold y1 constant if x1 is changing, because y1 is a function of x1. This is a messed up story here, right? This is not a composition of functions where we, there's we're multiplying matrices and we just have a shorthand for multiplying those matrices. No, not here at all. So that's what I'm going to leave y'all with. We'll resolve this next time, but this is a problem. Okay, see you later. Have a good one.